Process integration. Okay. All right, can you see the slides? Okay, good. Process integration. So let's continue. Process integration is the combination of all processes or most processes we discussed last time that you've learned before, right? From oxidation, lithography, etching, implant, diffusion, thin film deposition, CMP. So all these processes combine in certain sequence, in certain ways, um, in order to fabricate your semiconductor device. So be it integrated circuit, solar cells, uh, lasers, LEDs, and whatnot, right? Power device, more or less the content that I've mentioned in the presentation topic. um, Among all the devices, as I said last time, the most complicated one is integrated circuit. So you can tell the complication by the duration it takes, or in industry we call it cycle time. So that's the cycle it takes. It requires from day one till the very end of the process in order to finish your device or your product in particular. So if you look at IC, then typically it takes about 2 to 3 months, more or less, depending on the technology, depending on the device that you're fabricating, but more or less, that's pretty much the cycle time it takes to complete a typical IC. On the other hand, if you look at solar cell, so it typically requires 1 day in order to complete one cell. Well, no, one cell, but in batches, of course. Uh, so that gives you the what you call the perspective of how a cycle time looks like for a solar cell, for example, in comparison to integrated circuit. And I'm not sure exactly. We've discussed last time with Osram about the LED cycle time. So it is slightly shorter than IC, right? And then front end plus back end. And as far as I know, so far, perhaps solar cell is the shortest one. So you can get your complete device in like 1 day, right? So when you do your internship later on or company for your first job later on, you'll see how your device varies from other devices in terms of recycle time, process integration, combination of different processes, the sequence. It's going to be different, okay? It's going to be different. So we've covered last time about the front end and the back end on this page. So I have told you that normally when we talk about front end, we're talking about the wafer and then the formation of gate ox, the gate, the source drain, the well, perhaps spacer nitride we're going to see later on. So the moment it hits metal 1 and via 1, then we are talking about the back end of wafer fabrication already. Okay, so more or less again what I've told you last time, front end plus back end. So for example, kalau you dah dapat internship in Sotera, then maybe you are assigned, I don't know, maybe you're assigned to do front end or back end, for example. Okay, so then if you're assigned to follow a process integration engineer for front end, then your day in and day out, your daily basis is gonna be working. You're gonna be working on STI or well or source drain formation or gate ox. So you're gonna be looking on all these processes to make sure that they are well developed, well sustained, well controlled by process engineers of every single department, of every single process that we have in the process flow. So on the other hand, if you are assigned to do backend, if you're assigned to follow process engineer for the backend, so you'll be looking at via metal, IMD, BPSG until MONPAD, right? So they are altogether 5, more or less. Isolations, wells, junctions, gate stack, interconnects. This is the categories that we have for us to divide the process flow into specific modules, right? So we're gonna see later on where do you see the wells, where do you see isolations, junction, gate stacks, which one comes first, which one comes later. So this is your silicon wafer, more or less exaggerated vertically, so it's not that thick. So just to illustrate the usage of silicon substrate P plus and P minus. So in this case, your epi layer is P minus, is very thin. So the thickness is about 725 micron in total, just to exaggerate the thickness. Okay, so this is not a generic case for all the CMOS. So you may have different cases for different devices. So your pad oxide is the very first layer for the process flow. Kalau you tengok nanti, kalau if talking about Siltera process flow, then every single process yang you akan buat, dia akan ada process flow. So process flow ni is documented. So it's process flow. Kalau you are process engineers or you are process integration, you're gonna be dealing with process flow for every single device. So in Siltera, I'm not sure about this. If you're talking about process flow, then you need to be aware of process spec. The process flow is documented in process spec document, process spec. Usually they are coded as SP0 whatever. So as far as I can remember, it's coded as SP02 for process spec and blah 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 X followed by numbers. SP02 is usually for process spec. So for example, if you're talking about device A, technology A, device A, then if you open SP02 for device A, so then you open, you'll see an Excel file from the very first step until step 200, for example. So you'll see what is the exact process step from cleaning, for example, pad ox, then what's next, then what's next, then what's next, until the final day of the fabrication process, covering front end and back end together in a process spec. So usually during my time last time, we use SP02 to refer to be referred as a process spec for every single device. So if you have hundreds of devices, then you're going to have like hundreds of different documents for all the technology that you have in the fabrication process. So if you talk about a pad ox, for example, this is just an example of a pad ox, but it's not the numbers that I'm showing here is not a magic number. So it may differ from device to device. So, but the magnitude or the the magnitude of the number is more or less similar if you compare thickness of pad ox versus thickness of field ox. So the dimension is pretty much similar relatively, but it's not exactly 200 angstrom, for example. Okay, so in this case, a pad ox is about 200 angstrom or 20 nano. Silicon dioxide grown on surface of silicon. So we've learned about thermal oxidation in the very first part of this course. So it can be done by dry ox and wet ox. We've learned last time. So typically this one is dry ox. So this will serve as a stress relief layer between silicon and subsequent nitride layer. Okay. So in this case, we grow pad ox, a very thin one, on the silicon wafer. Next, we deposit silicon nitride, so 2500 angstrom or 250 nano silicon nitride Si3 and 4 is deposited using CVD process. So in this case, it's usually PE CVD, plasma enhanced CVD. We've just learned this one last week. This will serve as a polish stop layer during trench formation. So we're gonna see trench formation later on, and nitride serve as a polish stop layer. So whenever the polishing reaches nitride, so the process is gonna stop. So more or less it serves as a barrier to give you a signal that process has to stop. Next, so now we see it evolve quite fast. So we've learned pretty much everything before. So now we're trying to combine in certain sequence. Now we do patterning of photoresist. So you can see photoresist on the slide. So the red part or the pink part, more or less. Right, so you want to define the dimension of the trench. Remember, the trench is the drain, more or less, the hole. We discussed last time, trench. Soalnya kalau dekat setelah we call this shallow trench isolation, STI. Shallow trench isolation, shallow. So one of the most critical patterning steps in the front end in the process. So 0.5 to 1 microns of resist is spun, exposed, and developed. So this is basically CED, code, expose, develop. We've covered last time during lithography process. So you code the resist and then you exposed. For example, let's just discuss. Katalah sekarang ni kita punya resist is positive resist. Let's recall positive resist. So where do you expose on the resist? Which area do you expose? Do you expose the pink area or red area or the white area? Katalah ni positive resist. So this is the red area, for example. This is white area. Where do you expose? Let's recall our lithography knowledge. Positive resist. Anyone? Farah, Azwani, do you expose the white region or the red region? Red kanan, white tengah. Where do you expose? Positive resist. Farah, Azwani. Fazira. Fazira, you can unmute yourself. Which area do you expose? Let's recall our litho knowledge. Fazira, ada ke? Inas. Come on. Which one? Okay. I forgot, I think it's white. Is it correct, white? Inas, what do you think? Yishin, Nyam Yishin, where do we expose, white or red? Positive resist. Anyone? I need one answer before I move. Shahira. Ain, white. White. Okay, why white? Why do you say white? Yes, the answer is white. Why white? Kenapa white? What happens to positive resist during exposure process? During CED process. What happens to the resist? Soluble, yes, good. So the exposed areas will be soluble for positive resist. Therefore, the soluble areas will be removed during development process. Then you have the white region here. If you use negative resist, then the exposed areas will be hardened. Then you're not going to have this white area. It's going to be reversed. Okay. So kalau positive resist means these areas, area ni exposed. So this one block. This one blocked by the mask. Okay. So semua exposed. Ada illumination, right? So that's how you do the patterning again. So when you talk about integration, it's not only combining certain processes. You also have to recall why does it look that way. So for example, why patterning is like this. So what actually happens in the lithography process to be able to look like this. Okay, you kena recall balik lah apa yang you belajar. Then only you can relate to why you have such structures on this slide. Okay, so now we have done the patterning on the resist. We have exposed the central region. the left hand side, the right hand side. We block the light from the red region. So kita assume kita pakai semua positive resist in this integration on this slide. Okay, so easy for us to discuss. Next, so you've patterned your resist. What's next? Then you remove. You see that you remove the oxide. You etch the nitride. You etch the oxide. So the next step is called etch nitride and PET-ox. So by RIE process utilizing fluorine chemistry. So you use fluorine chemistry. So in this case, you need to recall what is RIE, so the anisotropy of the process, what are the typical gases being used in RIE process to enable etching of the nitride, etching of the PET-ox, right? So recall etching process in this case. So we now etch our nitride and PET-ox. So what's next? Then we etch the trench in silicon. We etch the hole or the drain in silicon. Using RIE process again, utilizing fluorine chemistry. So we define active areas of the transistor. Okay, so you dah nampak sikit-sikit dia bentuk sekarang, tapi tak habis lagi cerita dia. So you now can see a little bit of the transistor, but not yet. So now you can see the active areas of transistor to be observed very soon. So you now have the trench. Trench, you correct lubang, correct lubang. So what's next? So if you can notice here, you are actually isolating the trenches. You are isolating your device to device to device to device to your adjacent devices by using trench. Macam you tak longkang asingkan rumah, longkang rumah, longkang rumah. Next. So what's next? You remove the photoresist using oxygen plasma to burn off the resist layer. Oxygen plasma. So oxygen plasma, is it anisotropic or isotropic process? So what's the exact process we call here? Ingat tak the exact name of the process we learned last time during etching? What is this process exactly? Anyone? Hazika, can you recall the process name? The exact process name to remove the resist from this device. Apa nama proses dia? Anyone can recall? Aniza? What is the process here? If you have a question on integration, you have to be able to describe the process name, what's happening during the process, and what does it remove, what does it grow, and what do you get? So what's next, right? So what's the process name? Anyone? Tak lupa ke? Etching. Nabila? Nabila, this one? What's the process name? Mula huruf A. Saya dah bagi hint tu. So what's the name? During etching. During etching, mula huruf A. Saya ada ajar dua main proses kan, ingat tak? Etching and nama dia lebih kurang sama kan? Cuma tukar huruf A kat depan. Etching, okay? Etching. Etching, yes, exactly, good. Etching process, remove resist, oxygen plasma. So you have to recall the name, what is the details inside the process, using chemicals, using gas, isotropy, anisotropy, what does it remove, what it can remove, right? Stuff like that. So now using etching process, done. So you now get this structure, nitride, pattern, PET-ox, pattern, then you have STI or shallow trench isolation or trenches. Done. Next, fill trenches with oxide. So now its CVD oxide layer is deposited to conformally fill the trenches. So we deposit CVD oxide. So oxide layer by CVD process. Okay, CVD oxide means oxide layer deposited, not grown. Right? You can beza, okay? When you talk about oxide, it's either you deposit oxide by thin film deposition process or by growth process. Growth means thermal oxidation lah, thermal oxidation. Walaupun kita boleh panggil thin film deposition as a growth process also, but just to classify the two processes. So when you talk about CVD oxide, means it's grown, it's deposited. Kalau thermal oxide, kita tak panggil it's deposited, it's grown. Right? It's not deposited. Kita dah belajar thermal deposition process by PVD, CVD, E-beam, thermal, CVD, and multiple CVDs and stuff like that, right? So the purpose is to prevent crosstalk between transistors in the device. You can check later on, do some reading on why is it important to prevent crosstalk and what is even crosstalk. What is crosstalk in CMOS devices? What if you have crosstalk? So if you don't manage to deposit your oxide conformally, so what do you see on the crosstalk, right? So what do you get? So you now deposit the whole surface with CVD oxide. Next, right? So that deposit. So what's next? So polish trench oxide. So the surface oxide is removed using CMP process. So remember last time I talked about you have your slurry pad, macam basuh pinggan tu, right? Span basuh pinggan, then you have sabun, then you basuh pinggan, remove kotoran. So this one is like you do the CMP, you polish the surface using slurry, using a pad, macam apa, sponge. So you planarize the surface. So the goal is to planarize, right? Planarize. That's why we call it chemical mechanical polishing. Planarize polish. Planarize polish. So you can dapat satu layer yang sama thickness, more or less, right? So now you can see that your future PMOS on the left hand side, future NMOS on the right hand side are now isolated by using oxide from CVD, already polished. Done. Next, so you remove the nitride there. So you have the nitride there. So now you remove the nitride, a wet etch in phosphoric acid, right? Hot phosphoric. Wet etch. Tadi kita buat RIE kan? Kita buat RIE, then we did etching as well to remove the resist. Now we do wet etching. So it can either be dry or wet etch. So in this particular case, wet etch hot phosphoric is used completing formation of STI. So that's why I talk about STI. So this is considered STI. Done. Complete STI. Shallow trench isolation, fill with oxide, isolate two different devices, left and right. Next, we do patterning of photoresist for N-well formation. So kita pattern sekali lagi the resist. So in this case, we remove. So when I say it's patterning, so you should imagine that we first deposit resist here and resist here as well, full, left and right. Then we pattern. Patterns means we remove certain areas and we maintain certain areas. In this case, assuming positive resist, so these areas must have been exposed and developed, leaving this area alone, right? So kita nak buat resist, kita expose dekat left hand side, develop left hand side, so right hand side remains. So you have patterned the resist to be able to do implantation on the left hand side. Kita block right hand side, we're going to do implantation on the left hand side, right? Utilizing thicker resist to block implant. So thicker resist here means we have discussed last time, remember, when we talk about implantation process, you need to use a resist thick enough to block phosphorus or arsenic or boron dopants from coming into the layer. So this photoresist thickness must be thick enough to block, else you'll still have some layers dope in this region as well, which is unwanted, okay? Now we do ion implantation, the resist is thick enough. A deep high energy implant. So we learn about middle energy, low energy, high energy. So high energy is meant for deep implantation process. So therefore we use a high energy for deep implantation of phosphorus ions. So you use phosphorus ions to create a localized N-type region for the PMOS transistor. Okay, PMOS N-well. So you form N-well now on the left hand side, but you block the formation of any well on the right hand side. Done. So we strip off the resist from the right hand side. Done. Finished. So what's next? We pattern on the left hand side to be able to implant the right hand side on using opposite polarity. Okay, using opposite polarity. Sebab kiri PMOS transistor, kanan NMOS, right? So we pattern resist for P well formation. Just now it was N well on the left, now P well on the right. a non-critical masking layer, utilizing thicker resist to block the implant. Same concept like the previous process. Okay, so we now implant boron using deep high energy process in order to form well. So when we talk about well, it is never shallow, it's always deep, right? Relatively deep in comparison to your source drain formation later on. So that's why you need to use high energy implantation to implant boron and produce a P well. Strip off resist. Now you have your N well on the left, you have your P well on the right. Done. Next, so you anneal the well implant. This one is to repair the damage. Remember last time we've discussed about implantation is a process that involves damage. So if you use high energy implant, then you create more damage in comparison to middle energy or low energy, right? So you want to restore the crystal lattice in the silicon from monocrystalline, then damage your implant to be amorphous perhaps, and then you want it to be restored to be monocrystalline again. Just like what we've discussed during ion implantation process last time. To repair the damage and to also electrically activate the dopant. So remember, when you diffuse or when you implant dopants, tak kira lah P-type ke N-type ke, boron ke phosphorus ke, if you don't activate the dopants in the device, in the silicon, so they will just stay there in the lattice doing nothing. Dia akan end up as defect. Maksudnya you masuk boron, you masuk phosphorus, it will just stay there, but it doesn't contribute to conduction at all. So you want to alter the conductivity. You want to change the conductivity, the shear resistance, and stuff like that. So to be able to do that, you have to first electrically activate. Maksudnya you kejutkan dia lah. Masukkan dia, kejutkan dia. Kalau tidak, dia duduk tidur kat situ lah. So two roles of this process: to repair the damage from the implantation and to also electrically activate the dopants, right? So it also drives the dopant somewhat deeper. So remember last time we've discussed about diffusion more or less. So you have a factor of D, diffusivity, right? So we've discussed about diffusivity. So diffusivity of boron or phosphorus in silicon at some temperature in this case. So you are driving the boron somewhat deeper in comparison to the depth of the well intended during the implantation process, right? RTP is used to minimize dopant spreading. We've discussed about RTP last time in comparison to slow furnace heating. So kita boleh buat like spike punya annealing process. What you call? We produce pulses for like millisecond or certain seconds. Then kita akan guna halogen lamp to heat up the furnace. RTP furnace in this case using halogen lamp. Dia akan panas, cool, hot, cool, hot, cool. So it will minimize dopant spreading or dopant redistribution. So then we will get the well properties to be as close as possible to what we designed in the first place, right? Kalau you tak pakai RTP, then you're going to have your vertical component extending, a diagonal component, and also your lateral component expanding. Then you won't have a good control of your well formation. Next, SAC-ox, sacrificial oxide, we call it SAC-ox normally. So a thin 25 nanometer or 250 angstrom of oxide layer is grown. So the word here is grown. So kalau kita pakai grown, then what is the process that we use? Apa proses kita pakai? What's the exact process name? Grown. Saya baru sebut tadi kan? So what's the process name? Faika? Deposition or oxidation? Yeah, oxidation, right? Thermal oxidation. Grown oxidation. You punya first word tu dah okay, thermal, but the second one is not. Right, thermal oxidation. Grown, thermal oxidation, deposition, CVD ke PVD ke, right? Kalau deposition is always TFD process, thin-film deposition. Kalau grown, then oxidation process, right? So we grow a very thin layer of SAC-ox, 25 nano. Remove SAC-ox, tengok apa beza dia, SAC-ox. SAC-ox immediately remove in a wet HF solution, leaving behind a clean silicon surface, right? Clean silicon surface. So kita pakai wet HF solution. So now it is a wet etching process. in HF solution. So we learned last time that HF removes silicon dioxide, a thin oxide layer, right? So wet etch process, isotropic or anisotropic, this process? ISO or aniso? HF? One direction or all directions? With equal etch rates? Anyone? ISO, right? Yeah, isotropic. Isotropic, which means it will etch the silicon dioxide with equal etch rates in all directions, right? Isotropic process. Next, we grow gate ox. So thermal oxidation, grow gate ox. This is the most critical step in the process. Kenapa di critical? Because it's gonna sit below your gate, your polysilicon gate, for example, right? So it has to have a good integrity. Kita dah bincang tu kan, you punya breakdown field and everything when we talk about 386 last time. In 386, MOSFET punya property. So gate oxidation punya characteristic, it has to have certain properties, field strength, right, and other stuff. So therefore, it's the most critical step. A very thin layer, 20 angstrom to 100 angstrom, so 2 to 10 nanometers. Oxide layer is grown that will serve as the gate dielectric for both transistors. Must be extremely clean and grown to a very precise thickness. So 1 angstrom, so that means about plus minus 0.1 nano. So if you draw your SPC chart, so if this is your 5 nano, for example, then your plus minus is only like plus minus 1, 0.1 nano on the SPC chart, right? The fluctuation that it can tolerate. Else, it will just be considered as a problematic layer. Next, so you've got your gate ox now. Next, polysilicon deposition. Polysilicon deposition by CVD process. By CVD, right? Deposition. Huh? So thickness of about 150 to 300 nano. More or less, right? 150 to 300 nano or 1,005 to 3,000 angstrom. Okay. So polysilicon deposition. Next, patterning to define gate electrodes. So your polysilicon here is going to be your gate. It's going to sit on a gate ox. So you're going to, kalau you recall balik MOSFET structure, then you're going to have source, drain, gate ox, gate. So this is your polysilicon gate, right? Sekarang kita belum define lagi dia punya dimension, so it's just a blanket polysilicon layer. Next, now we're going to define by lithography process. So this is where you see the role of perhaps EUV, ARF, DUV to define the small feature, the technology node, for example. If you talk about sub-5 nanometer, 532, then the EUV is going to define the dimension of your gate. That will determine the speed, the quality of your device, right? So this is the most critical patterning step in the process. Precise sizing of the polysilicon gate is a first order determinant of transistor switching speed. Now we're talking about what? 2 gigahertz, 3 gigahertz. So it's defined by this guy, right? Defined by this guy. So if this guy is not correct, then your speed will not be correct as well. The highest technology patterning system are DUV. So this time it's DUV, but now it's EUV, right? EUV along with thinner than normal photoresist. So when you go for smaller technology node, so your photoresist thickness is going to be low as well, correspondingly. So due to critical nature of the layer. So we now do the patterning of your photoresist on the polysilicon, right? So if you can recall, last time we did discuss on the solutions to the case study, right? Remember, kalau kita nak define your capability smaller than your equipment capability, 500, then you want to pattern 200, for example. 200, you want to pattern 100 nanometer, for example. So this is more or less the structure that I've discussed last time. So we pattern polysilicon by using resist, right? We need the resist to pattern polysilicon. So you now coat the resist, expose these areas, expose, you block this area, then you remove all the exposed regions. Then you're going to end up with that resist line. Okay, that resist line, Okay. Next, apa jadi? Etch polysilicon and strip resist. There to there. Etch polysilicon first, right? Etch polysilicon, but the area that you want to maintain will be blocked by photoresist. Then only you etch photoresist, then you will be defining your gate, right? Etch polysilicon and strip resist. RIE process using fluorine chemistry is used. RIE, fluorine chemistry. So this completes formation of your gate stack. Remember the modules, you have interconnect, you have gate, you have isolations, right? You have altogether 5 modules. So this is the formation of your gate module, right? So you have polysilicon gate on gate ox on your bottom structures. Okay. Next. Apa jadi? Poly reoxidation, right? Poly reoxidation. A thin layer of oxide is grown, where the word is grown. So oxidation then on top of the polysilicon to act as a buffer between poly and subsequent silicon nitride layers. So you're going to have nitride on the sides before we proceed with the back end. Next, you pattern the resist for NMOS transistor tip implant. So let's see how does a tip implant looks like. So you pattern one side, so that means you expose on the right hand side, you block on the left hand side, just by the same lithography process. So you implant arsenic. So in this time, you use low energy implant because you need to form a very shallow implanted layer. So the first one is now we use high energy implant in order to form the well, deep layer. Now we're going to form the tip only. The tip means very shallow, therefore you don't have to go for middle energy or high energy. Low energy should be enough. Low dose implant of arsenic, for example, begins the formation of an NMOS transistor source and drain. The tip will serve as to reduce hot electron effects near gate region. Okay, let's see how does it look like. So you pattern your tip here and there. So that will define your source and drain for your right hand side transistor, but your left hand side will follow next. Next, done. Strip the resist. So you're ready for your next implantation on the left hand side. You coat the right hand side, you develop the left hand side using the very similar lithography process. So now your left hand side is exposed. Now we implant PF2, shallow, low energy as well. So just the opposite side of the right hand side process now. So you now form your source and drain or your left hand side transistor. Done. Strip resist. You're now complete with the left hand side and right hand side complete transistor. Okay, next is to deposit silicon nitride. So deposit silicon nitride using CVD process, thickness 120 to 180 nanometer. So you have seen issues like a step coverage last time, omnidirectionality or less omnidirectional. You can see the coverage on the side now, the shoulder slightly thinner but thicker on the wall, right? On the shoulder and on the side it's quite thin, and it's thick on the wall because it just accumulated on the wall, so therefore it forms a rather thicker layer. So that's how it looks like on the transistor now. Your nitride is deposited blanket. Blanket means the whole surface, okay? Next, etch nitride and form spacer sidewalls. Carefully control RIE etch. Thin nitride is removed from the horizontal surface. So you remove, if you compare previous and this, see what's the change. You remove the horizontal part of the nitride, okay? Horizontal part is removed. The sidewall remains. So this will precisely position the implant to form the transistor source and drain. So see what's next. So you have now nitride on the oxide beside or on the polysilicon. So we pattern again using lithography process. Then you go for high dose, shallow but high dose. Tadi kita pakai low dose kan? Sekarang kita pakai high dose. Then you're gonna form a tip like this. Tadi kita dapat macam ni ya. Right, sekarang kita dapat macam tu. So bear in mind, this is not for all devices. So this is only one example of a device. So you may not have such a source drain structure. You may have just a one tape design. Okay, tak semestinya macam ni. So this is only one example of how it looks like if the device looks like this. If it's not, then your process will change accordingly, right? So shallow but high dose implant of arsenic completes formation of heavily doped N transistor on the right hand side. The spacer shadows implantation near the gate region. Right, yeah. Anak saya cakap dah lapar. Let's go for another 5 to 10 minutes, right? Implantation near the gate region, right? So next, strip the resist, do the other one, do the opposite one. Implant shallow high dose BF2. Sama juga, just the opposite side. Strip the resist and anneal implants. Use RTA process to virtually eliminate dopant migration. So you are now complete with your device. Okay. All remains is to connect them together. So they are not yet connected, but you've completed the core device. So sekarang kita nak tengok the interconnect, the back end. So what's next? Strip off your oxide. Quick HF dip in HF to expose bare silicon in the source gate and drain areas. So now kita nak start kita punya back end process. Kita nak start deposition of titanium using sputtering process. Titanium sputter to deposit 20 to 40 nanometer of layer of titanium. So metal. So how would you deposit titanium by sputtering? Are you going for DC or RF? DC or RF? If you have metals, then would you use DC or RF? Anyone? RF? Well, you can use RF, but can you use DC as well? Okay, minimum you can use is DC, sebab kalau you punya layer is conductive, in this case metal, titanium, you can use at least DC. You don't have to go for RF. Tapi RF can also do metal deposition. But DC cannot do dielectric deposition. DC can only do metals. RF can do both, right? So DC can do metals, cannot do dielectric, like silicon dioxide, silicon nitride cannot. But RF can do both metals and dielectrics. Next, titanium silicide formation. RTP in nitrogen ambient at 800 degrees C cause titanium to react. So titanium will react with silicon to form TiSi or titanium silicide process. Okay, titanium silicide layer. Right, the process is aligned to the silicide to the exposed silicon. Aligned silicide to the exposed silicon is called self-aligned silicide or salicide. Silicide, right? Kalau you pergi, you join Cetera later on, you can see the punya room name. The room name is named after the process, right? Saya tak ingat tingkat berapa, tingkat 3 kot. Ada bilik silicide, damascene, and stuff like that, right? You can see later on the process name is used to name rooms, meeting rooms, training rooms. Okay, so titanium silicide done. Titanium etch, unreacted titanium, which has not reacted with silicon, is removed during wet etch in ammonium hydroxide and hydrogen peroxide. So titanium silicide remains. Titanium silicide is there to provide ohmic contact because between silicon and metal, right? Ohmic contact. So in order to do interconnection, you need to have ohmic contact between your silicide and your metal later on. So I'll go for another 5 minutes. Next, so you have your titanium silicide on top of your gate source drain. So dia akan connect between your gate source drain and the metal. Kalau you tak pakai ohmic, then you will end up with Schottky contact. So that will not be good. Next, you do BPSG deposition. Silicon dioxide doped with small amount of boron and phosphorus to enable reflow, and getter. So you need to do gettering as well in this process using CVD. So BPSG using CVD. Borophosphosilicate glass. Borophosphosilicate glass, CVD. Using CVD. So about 1 micron, this is not correct for all cases. It depends on your device. This is only the example, okay? Electrically insulate the device from the first metal layer. So the role is to insulate. So it's a dielectric layer to insulate the device from your first metal layer. So we're going to see the first metal. So sekarang dah masuk backend lah. Tadi front end dah habis. Sekarang backend engineer punya job lah. BPSG, you plannerize using CMP to make sure that you don't have bumps and topography. That will be a problem for your metal formation later on. You want it to be completely flat, right? So you use CMP process. Next, you do patterning using photoresist. So you open certain areas for the contacts, VR and metal, VR and metal, VR and metal. So this is how you define the subsequent steps later on to connect your device, gate, source, drain, to your metal. You expose this area, expose in lithography, expose, and you block, right? So you open the contact. Next, you etch BPSG. So you define the pattern. Now you etch BPSG down to the gate source drain, right? So sekarang you open source drain first. Use RIE, vertical process, anisotropic using fluorine chemistry is to achieve vertical sidewall. So you etch sampai ke bawah. Sekarang you tengok you punya lubang sampai ke source and drain. Then you can put the contact. Next, you strip the resist. Resist is never intended to be there forever, right? It's just a medium to do patterning. So it will not be there at all in your final device. So now we remove the resist, you are left with pattern BPSG. Next, you coat, you sputter titanium nitride, TIN, metal layer is about 20 nano. So it will help subsequent tungsten layer to adhere to the oxide because you have oxide there. So you sputter tinitride, we call it tinitride usually in the fab, tinitride or titanium nitride. Next, you deposit tungsten. Tungsten will be the contact, will be the metal contact. So tungsten, remember last time I labeled W, tungsten. So by CVD to fill in the contact holes, saya akan cover sampai metal 1 and then I'll just stop. The thickness will be half, at least half of the diameter of the contact, right? So it depends on the device design. Next, you remove by CMP. So sekarang tinitride, remove tinitride. So you are left with a planarized surface containing contacts at the designated area. So these areas are called plugs, tungsten plugs. Plug to contact lah, nak connect. Next, metal 1. So we now deposit metal 1. So you form the contact now. Each interconnect layer is actually a sandwich of different layers. So you sputter your first metal layer. So this layer, metal 1, contains of few layers in between. So you have titanium 20 nano, you have tinitride 50 nano, aluminum copper 500 nano, tinitride again 50 nano. It depends on what sort of contacts you use for your device. So it's not true for all cases, right? For this case, it's true, but you normally have like multiple layers with different role. The first one, for example, is for electromigration. We're going to see in interconnects later on. Second one is diffusion barrier. Third one is the main conductor to do the conduction. Fourth one is anti-reflective coating. So even though it's not an optical device, you still have to have this layer to do some anti-reflection mechanism. Next, you pattern the resist. Again. Next, you etch the metal 1. Etch metal 1 using RIE, fluorine. Next, you remove the resist. You dapat metal 1 being patterned, so your first interconnect layer is ready. So I'll just stop here first. So you now have your metal 1. So tomorrow we're going to talk about what's next after metal 1. So you can see now that your integration has changed your process from PET-ox, the very first layer, go to all the processing, sampai you dapat metal 1, which connects your source, your drain to the metal layer, right? So this is how your carriers are going to be extracted to the outer circuit later on, but it's not complete yet. So we're going to have like more layers on top, more patterning, blah, 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 sampai habis, huh? So we're going to see until metal 2 lah, overall in this particular lecture, right? So you're now with metal 1. Yeah, metal 1. So we're now on page 60. We have about 17 to go tomorrow. Then I'll upload also on the metal interconnects. Maybe we can finish tomorrow as well. If not, then perhaps Thursday. Then we're gonna finish integration and everything in this week, inshallah. So I'll give you one more lecture on fabrication process for solar cell, particularly silicon. After we finish the interconnection and contacts, then I think we should be done by this week, more or less. Okay. All right. Any questions for process integration? We'll move on tomorrow after metal 1. Okay. Can you follow so far on how do we do integration? Okay, guys. Okay or not okay? Anyone? Can you follow so far? Okay, so far, right? Okay. So now you can see combination of multiple processes to get your final device done, right? So I'll see you tomorrow then to continue from metal 1. Bye-bye, take care. Assalamualaikum.